In this video, we will see how to delete a node in a binary search tree. So first of all, what is a binary search tree? It is a binary tree, so it can have at max 2 children, and it maintains the search property. That is, all the nodes in the left subtree has a value less than the root node, and all the values in the right subtree have a value of more than root node. And this is true for all the nodes. For example, this is valid for this node. So all the left subtree will have less value than 5. Similarly, it's also valid for this node. So left side will have smaller value. So search property is maintained for all the nodes. So in this we have to delete a node. So we will be given one value. For example, let's say we are given the pointer to this root node, and we are also given a value to delete, let's say 3. So first we have to search that value, and then we have to delete that value. These are the two steps. And if that value is not present, we will not do anything, and we will leave the tree unchanged. So let's see what are the different scenarios and what we should do in each scenario. So first case is that node is not present itself. So let's say we want to delete 15. We come here, we compare that 15 is more than 10, so we go to the right side. Then we see that 15 is more than 12, so we go to the right side. But right side is null, so 15 was not found, so nothing will be changed. Next case is, so case 1 was value not found. So in this case, nothing to be done. Second case is node that we want to delete, node containing the value that we want to delete is leaf node. So let's say we want to delete either 4, 9 or 12. So first we will search it. So let's say we want to delete 4. So what we will do, we will compare with root. It's less than root, so come to the left side. We will never go to the right side again. So either we take the left or right, not both. So again 4 is less than this, so we come to the left side. And now 4 is same as the current node. So we have to delete it, so simply make this node null. So this node is gone. And the left of 7 is now null. So this node effectively goes away. So this is the simple scenario where it's leaf node. Then what we do, find the node or node pointer and make it null. And we are done. Then we have another scenario where it's not a leaf node. For example, let's see here, this is the third case where we want to delete non-leaf node. And let's say we want to delete 7 here. So we compare with 10, it's less than 10. So we can go here, call the same function, delete function that we want to implement. So delete root if, and also there will be one value. So if root value is more than value, then we have to delete in left part. So root dot left equal to delete root left and the value that we want to delete. So this would return a node pointer, this delete call, the root node. So in this case 7 was less than root value, so the left of 10 will become whatever is the root returned by this delete on its left. So we believe on the recursive function to do its job. So this recursive function job is to find and delete a node in the tree rooted at this node. So now we know that subtree is in the left part since its value is less than root. So we call that function again on its left subtree and pass the value. So assuming that this function works correctly, it will return the new root, updated root of the tree. So it will delete 7 from this subtree and return the updated root, and that will be the left of 10. And similarly you can write the case where this value is less, then delete the right. And third case will be when root val is same as val. In this case we are at the current node, so we have to delete the current node. So when this delete is called for this subtree, then in this call root will be 7. and when we compare its value, it will match. So it will enter this scenario. That is, we have to delete the current node. So we check if its left and right are null, then that will be the previous scenario, that is leaf node. So that is the way to check here also. So I have not written the code, but that is how we will check. So if its left and right are null, simply make it null. But if its left is present or right is present, then we have to do some work. So let's say left is present. So in that case, we will find the predecessor, in order predecessor. So one of the properties of binary search tree is that if we print the in order traversal of this tree, then we get a sorted order. So if this is a root node, all the values in left subtree will be here, all the values in right subtree will be here. And in this tree, in this subtree, we have to delete this root node. So either you delete the exactly predecessor of this or the successor of this. So whatever is the value, copy it here. So 4 comes here and then delete it. Now it's a valid, since we are finding the largest in this part. So this predecessor is the largest in this part and the successor is the smallest in this part. So if you copy either this or this to this node and then delete this, the search property will be valid. But if left is not there, so if left is there, then find the predecessor, copy it here and delete that predecessor. And we will do each of these recursively. So now let's look at the case where left is not present. So it's up to you. First you check right or left, it's up to you. So if you first check the right, you have to pick the in order successor. In order successor is the smallest among these. In order predecessor is the largest among these. So if you copy one of these to this root node and then delete this, search tree shall be valid. So here let's say we have to delete 7 and there is one mistake here. So this should be 9 and this should be 8. Since this is left of this, it should be smaller. So we have to delete 7 here. So we come here, we call delete 10 7, and this 10 is not int 10 but node 10. So let me circle it. So it will check if its value is more than this or less. So this value is less than current node. So 10 dot left equal to delete 10 dot left, and I will write 7 here with this circle denoting the node, and the value is 7. Now it will check that 7 matches with the current node. So we have to delete this. So we check if 7 has left or not. If it has left, then find the in order predecessor. If it's not there, then so first of all check whether it is leaf or not. So if not left and not right, then make it null. It's a leaf node. If left is there, find the in order predecessor, copy its value here and call the delete on in order predecessor. And in this case, right is there, left is not there. So root val equal to in order successor of this node. So in order successor is what? You go right once and then keep going left. So you come to 9 and keep going left until you reach until the left pointer is null. So that will be in order successor, and in order predecessor will be go left and then keep going right. So this will be the largest in this subtree. Why? Because the right of this will be larger than this. In the left, everything will be smaller than this, and we are going right, and going right means larger value. So keep going right until right is null. So this will be the largest value in this subtree, left subtree. So it will be in order predecessor. Similarly here, we go right to enter the right subtree, and anything to the right of this will be larger than this. So we keep going left. Going left means a smaller value. So this is the smallest in this subtree, right subtree of 7. So find the in order successor, which is 8. So its value now becomes 8. Then its right will be calling the same function delete on its right subtree, that is root right, and we have to delete in this case this. We have copied the value here, now we have to delete 8. So just pass that value root.val, and it will take care of this. It will again come here. See that 9 is here, so 8 is smaller, so it will go left. And again 8 matches, then it checks whether it's leaf or not. If it's leaf, it will just make it null. So ultimately the final deletion will happen only at the leaf level. So this is how we handle all the cases. Now let's write the code for this. Let's analyze the time complexity also. So what we are doing, we are starting from root, and then depending on the value, we either go left or right, not both. So in worst case, we have to pick the branch with the highest depth. So time complexity will be of the order of height. If it's balanced to a good extent, then it will be log n, where n is the number of nodes. So if it's balanced, then the height will be of the order of log n. So that's why time complexity will be of the order of log n. And space, we are not using explicit space, but if you count this recursion stack, space taken by that, then it again can be order of height. So let's write the code. If root is null, then nothing to be done. If value is more, then we have to delete in the right part. So left part and the root itself will be unchanged, only right will change. And very similar to this will be the left case. And else means we have to delete the current node. So here we will have to find the in order successor or predecessor. So first check if it's leaf or not. That will be the good case. If not, root dot left, and not root right, then it's leaf. Then just make it null. If left is present, find in order predecessor. And we will define this function shortly. And then so this value is now updated with the value of in order predecessor. So we have to find and delete that value in the left part. And the equivalent case will be or we can ignore this. If both are not null and left is not null, then this else means right is not null and left is null. And we will also define this function. So predecessor, we have to just go left and then keep going right. So root equal to root dot left, and we are already checking for the validity of root, so it will be only called when this root left is valid. So no check required for root. And then while and when right becomes null, return its value. Very similar will be the in order predecessor, in order successor. So let's see. And the solution is accepted, and it's better than 90%. So there is some optimization that you can make here. So for example, here we are finding the in order predecessor. So it traverses from this root node. Let's say we were finding the in order predecessor of 3, or let's take a bigger example. We were finding the in order successor. Let's see, we have a right subtree, and it went here, then here, so it traversed this part. So we are calling this 8.write equal to delete in this part. So that will again traverse this part. So you can save some time there by keeping track of the parent node where you found that value in order successor, and then directly go there. So that will be some optimization here. So let's complete this in Java and Python. So I don't think here much change is required. And the Java solution is also accepted. Finally, we will do it in Python 3. So you can see some difference here. That is because we preferred in order predecessor over successor. So if you choose successor, your different answer may vary. Since you pick the largest of left or the smallest of right, that will make a difference. And the Python solution is also accepted.